Energy Economic Seminar Series. So this is hosted jointly by Columbia, Stanford, Cornell, and MIT, and we're really excited to see so many of you here from across institutions. We're also delighted to have Bob Pindyck starting off our series, and he'll be presenting the welfare costs of catastrophes, lost consumption and lost lives. And we're really keen to try to retain as much as possible the interactivity of an in-person seminar. So please do feel free to ask questions throughout, and you can do so directly by unmuting your microphone to ask questions directly. So there's no need to use the chat or the hand-raising function. We're trying to keep it as much as possible, retaining the spirit of an in-person seminar. So the seminar will be recorded and posted online after the seminar, and will run for 90 minutes. And if this is still okay with you, Bob's very kindly agreed to stay in the Zoom room for a few minutes afterwards for some more informal discussion as well.
Yes, sure.
So with that, we'll hand over. We're really looking forward to your talk, and over to you.
Well, thank you. And yes, interrupt me anytime, and you can't throw tomatoes at me because you're too far away, but feel free to interrupt and ask questions or object or whatever. All right. So this is work with Ian Martin from LSE, and it's an extension of work we did earlier. So we had a paper we wrote, it was published about 5 years ago, on averting catastrophes. And the basic idea is that we looked at in that paper is that society faces multiple potential catastrophes. Climate change is one of them, but there are others: nuclear terrorism, pandemics, and so on. And then the question is, which one should we avert? And suppose that if you did a cost-benefit analysis for all of them, each cost-benefit analysis would say that the benefit of averting it is greater than the cost. Well, does that mean we should avert all of them? And we show that no, that's not the case. And in fact, it's quite counterintuitive in terms of which ones you should avert. We use the willingness to pay as a measure of the benefit of averting a catastrophe. And we use a tax, tau, on consumption as the cost. So what we do is we say, look, the willingness to pay is the amount of consumption, percentage of consumption that society would permanently give up in order to prevent this catastrophe. And tau is the tax that we pay in order to prevent the catastrophe, right? And of course, willingness to pay is just a reservation price. It doesn't mean it would cost that much. That's the most we would be willing to pay. And in that paper, we also talk about not averting, but reducing the probability or ameliorating. But I'm going to focus on just averting for now. And we looked at, N types of catastrophes, and we came up with a rule for determining the set that should be averted. But the problem with that paper is that everything was based on the loss of consumption. And those of you who are familiar with the so-called consumption disaster literature, Robert Barro's work, I've written a paper on this with Neng Wang. There's quite a few papers out there now. So there's a literature out there on, they're really generic catastrophes, generic disasters in which we lose consumption. Consumption is reduced by some fraction. And there are all kinds of papers on this now. But all of it is based on a loss of consumption. Everything out there is based on the loss of consumption, not death. But we know that a lot of catastrophes kill people. And so the issue that we wanted to deal with is death. How do you incorporate death and look at welfare effects? I'm going to just show you 2 slides from the earlier paper, because this way I can say I told you so. So this is a slide that shows that if society's coefficient of relative risk aversion is 2, and this is the willingness to pay, and this on the bottom, the horizontal axis is the tax that it would take to avert the catastrophe. This straight line is the 45-degree line. So anything above that line has a positive NPV. A circle means you should avert it, and a X means you should not avert it. So in this particular example, you should avert 5 of the, we have 7 catastrophes here. You should avert 5 of them, but not earthquakes or climate. If we increase the coefficient of relative risk aversion, then we should avert a climate catastrophe, but not bioterrorism, not storms, not earthquakes. The only thing I want to point out is that in this little exercise we did, virus, that's a pandemic, is at the top. The highest benefit cost ratio is for a virus. There you go. So you see, we predicted everything that's going to happen. We wrote this paper, we started this paper 2 years ago. And the draft you've got now was written before COVID. So this was very opportune. We actually had a capital gain as a result of COVID, I'm sad to say. All right, so here's how we look at this. We're gonna have N consumers who are identical. We do not worry about people's age. We don't worry about their income. N identical consumers, and everybody consumes the same amount, capital C. So capital C is a per capita consumption measure. No catastrophes. If life was nice, consumption would grow at a normal rate G, and the population would grow at a normal rate little n, okay? And we're gonna normalize so everything starts at 1. And there are 2 types of catastrophes that we'll worry about. A consumption catastrophe, consumption falls by a random fraction phi. And this is a Poisson arrival with arrival rate lambda c. And a death catastrophe, where the population falls by a random fraction psi, and it has an arrival rate lambda d. And those people who don't die, who remain alive, their consumption doesn't change. Okay, it's only the people who die. Now, we want the willingness to pay to avert each type of catastrophe. What's the most society would pay to avert each one? And we want the willingness to pay to avert both of them. So that's the task that we have. All right. So we need a framework here to look at welfare. And we're going to say that a living person who consumes gets utility U of C. And a person who dies gets utility V of C. And for now, V of C is completely general. Now, some of you are upset and you're going to say, well, how can you have utility when you're dead? And let me say 2 things. First of all, you make bequests. You know, people make bequests, and the government also redistributes wealth. So if you die, whatever wealth you had, some of it goes to whoever you say it should go to, and some of it goes to the government. So there's welfare there. But I also want to point out, for people who don't like this idea of utility of death, the entire literature on VSL, everything that started, way back 40 years ago, is based on a utility in the living state and a utility in the dead state. There are 2 states of nature, and we have to compare utility in both states. So there's no getting around this. We can't just, later I'll talk about how we're going to model utility of death, but there's no getting around it. It's inherent in the whole system, the whole literature that VSL is based on, and so on. So we'll look at this. We have to figure out what this utility is, and we're going to derive an expression for it. So N is the number of people alive, and I'm going to use an asterisk if nothing bad happens. So N star is the number of people if nobody dies. There are no catastrophes. Therefore, N star minus N is the number who have died. So total welfare is, well, the number who are alive times the utility of each one based on the consumption they enjoy, discounted, and the expected utility, V of C, that the consumption they enjoy, even though they're dead, of the people who are dead. N star minus N is the people who are dead. Okay? This should cheer you up. Some of you thought that when you die, it's all over, but look at this. These people are consuming. All right. There's a very, very important assumption here. And that is that utility, when alive, is constant relative risk aversion. And, obviously this always simplifies life, but it's very important for this particular model. We tried working this thing out with recursive preferences, different kinds of, hyperbolic absolute risk aversion, more general preferences, and it's difficult. The constant relative risk aversion, everything gets simplified. Everything falls through very nicely. So I got to say that, this is something we're assuming, and it's a critical assumption. It's not just something that, hey, we can get rid of this easily and I can give you the results without this. Okay, so and eta is the coefficient of relative risk aversion. Now, we have to look at this issue of what happens to somebody who dies. What's their welfare? And there are different approaches that people have used. So one approach is to assume that when they die, their consumption goes to 0. The problem is we're going to assume that the coefficient of relative risk aversion is greater than 1. The reason we're going to assume that is because that's what's consistent with all of the macroeconomic literature and the finance literature. All of the literature suggests that that coefficient of relative risk aversion is something between 2 and 5. Well, if it's greater than 1, then utility goes to minus infinity when consumption goes to 0. This won't work, can't do this, okay? The philosophers have something they call critical level utilitarianism. The idea is that there's a level of consumption, CM, a minimal level that's just sufficient to sustain life or tolerable life. And so they would assume that consumption drops to that level. The problem is that we want to allow consumption to drop to anything. We don't want to be constrained by that. And anyway, how do you decide? I mean, what's the utility that's necessary to sustain life or tolerable life? So we don't know how to get that number. So we don't feel that this is a way to go either. Another approach is simply foregone utility. You die, you lose whatever utility you had when you were living. But this actually underestimates the loss, and let me show you why. Suppose the coefficient of risk aversion is 2, C is 1, so utility is minus 1, okay? Is the welfare loss just the loss of this utility? Is it just minus 1? Well, to see, let's suppose that consumption drops by 75%, goes from 1 to 0.25. Then utility is minus 4, and the welfare change is minus 3. That's much bigger. And for most people, 25% of normal consumption is preferable to death. Most people, if you said, look, we give you a choice, you die, or we lower your consumption to 25% of what it used to be. I don't know about all of you, we could do a poll, but we're not. Most people would say, I'd rather live, okay? So simply getting rid of the utility that they had before they died is going to underestimate the utility loss. Now, nonetheless, the common approach is to add a positive constant to the utility function, like this. And then death means that consumption drops to a level so that indeed utility is 0. And then that gives you a value for that value B. I'm sorry, for that value epsilon. Now the problem is this constrains things. This constrains the utility loss. You have to do this. Those of you who remember the whole very, very nice paper by Bob Hall and Chad Jones in the QJE maybe a decade or so ago about the value of health. They had to do this because they had to look at the trade-off between reducing your consumption and avoiding death. So to do that, they needed to have something like this. But we don't care about this. All we're doing, and we're not looking at different people, we're not making comparisons of rich countries and poor countries. We don't need to do this. We can be more general. So we're not going to do this. What we're going to do is take advantage of constant relative risk aversion. And it turns out that with constant relative risk aversion, we can treat death as a utility loss from dropping consumption to some fraction, with that fraction epsilon determined by the VSL. And that we have to get into the value of a statistical life. We have to get into that to see how this is going to work, okay? So I got to remind you what the VSL is. It's the marginal rate of substitution between wealth or income or discounted consumption over a lifetime, something like that, and the probability of survival. Now I'm going to use P, little p, to be the probability of death. So 1 minus P is the probability of survival. Often in the literature, they switch it around, but we're going to find it easier to use P to be the probability of death. So this is the definition of the VSL, and this is what it looks like. And if you wonder where that comes from, very easy. Just take your expected value. Your expected value is your utility of wealth times the probability of surviving, plus the utility of being dead times the probability of not surviving, and take the total derivative and set it equal to 0. Total differentials, you get this expression. So it's very simple. So what we need, and again, the VSL loses meaning if we don't have this V of W. We must have V of W, okay? We need to have something that describes utility in the dead state. Otherwise, we can't meaningfully look at a marginal rate of substitution.
Say, Bob?
Yes.
Can I go
Larry,
back to this issue of consumption losses versus loss from death? If you stick with the constant relative risk aversion utility function with eta greater than 1, then utility approaches negative infinity as consumption goes to 0, right?
Yes.
So
we're not going to let it go to 0.
But one of the things you're comparing now is catastrophes involving death with catastrophes involving just consumption losses. Doesn't this bias the importance of the latter? Because now if you have a consumption-oriented catastrophe, the cost can be huge because of this infinite negative utility aspect.
Well, first of all, we're not letting utility go to 0, so nothing becomes infinite. We're not letting consumption go to 0. We're letting consumption drop when you die. A consumption catastrophe is different. Your consumption drops by some random amount because there's an economic.
I guess my question then is that random amount ever approaching 0, which would make the consumption component, the consumption catastrophe, terrible?
Oh, we have to model the consumption catastrophe. I have to tell you what it looks like. And it's going to be very simple. A consumption catastrophe is what you see in the standard consumption disaster literature. It's just a drop in consumption by some amount, random amount.
It's never in the range of approaching 100%.
Consumption's not going to drop by 100% in this model. Okay. All right, so this is the VSL, utility in the living and dead state. They're measured in utils. The marginal utilities are measured in utils per dollar. So the VSL is always measured in dollars, and it is invariant to affine transformations of either utility function. So it's very nice in that sense. That's why it's used so widely. And as in the literature, the VSL, we're going to assume it's an observable multiple of wealth. The multiple is S. Now, those of you who know, there's a huge literature on the VSL. The way it's done is, we look at their behavior. What kind of jobs do they take, for example? And we see how that affects their lifetime consumption or their wealth or something like that, okay? And we usually express utility as a multiple of wealth or lifetime consumption discounted, something like that. So that's what we're going to assume. It's S times W. And the studies out there find that S is around 7, in the range of, let's say, 3 or 4 to 10, but 7 is a good midpoint value. If you use 7, you're going to get a VSL in the United States of roughly $10, $11 million. Those of you who know the literature, you know that's the number that the regulatory agencies use. The Department of Transportation uses that. The Environmental Protection Agency uses that. These are the numbers they've traditionally used, around $10 million. And those of you who looked at some of the recent papers on COVID, cost-benefit studies of COVID have seen, again, they're using $10 million to value a lost life in COVID. So 7 seems to be the value that kind of in the middle of what comes out of these studies. Now, we're going to see whether this makes any sense a little later. And I'm going to show you that it may not make a lot of sense, but we'll get to that. But this is the number that's used, and it's used by the government and other governments as well. All right, now we need to find utility in the dead state. And so since S is observable, we can approximate the probability of death. Remember, this is the a priori probability of death as 0. Let me just back up here. Here's the VSL. P is the probability of dying, all right? And we're going to look at the marginal rate of substitution when that probability is very small, so we can approximate it as 0. Most of you look very healthy. Those of you I can see on the screen, I would say your probability of dying in the next 6 months is very, very low. So we're going to make P0, and then that equation for the VSL gives us a simple relationship between utility when dead and utility when alive. And this is what it looks like. Very simple. Now, of course, utility comes from a flow of consumption when you're alive. And we're assuming that consumption growth is IID, independent increments, independent increment distribution. And that means that consumption and wealth are proportional to each other. So in any growth model, when you have consumption growing as IID, consumption and wealth are proportional. So there's a paper by Robert Barrow on this. My co-author Ian Martin wrote a paper on this. There's several papers that show this. The constant of proportionality doesn't really matter because the VSL is invariant to affine transformations. So we don't really care what that constant is. It means that we can work with either consumption or wealth interchangeably. We can use one instead of the other, and that's what we're going to do. We'll start out with wealth. So here is utility of wealth. Instead of consumption, we're just using W instead of C. Here, let's substitute this into the VSL expression that we had for V of W. We now get an expression for utility in the dead state. This is what it looks like, all right? It depends on the VSL parameter, coefficient of risk aversion, and this is what it is. This is utility in the dead state. And what this says is that the welfare loss from a death that occurs is what happened. The welfare loss is the same loss that if a living person's wealth falls from W to epsilon W, or equivalently, because of the nature of the VSL, because consumption falls from C to epsilon C, and this is the expression for epsilon, all right? So we can express utility in the dead state as utility of consumption in the live state, just multiply consumption by epsilon, where epsilon is given by this expression. And now we have total welfare. Total welfare is the expected value of N, number of people alive, times their consumption, number of people who are dead, times their utility, which is epsilon C to the 1 minus eta. People alive, we have to raise C to the 1 minus eta. All right, so this is now social welfare. The welfare of those alive and the welfare of those who are dead. All right, now, we need to say more about what's happening over time. I mean, what's going on here over time. So now we have to make this dynamic. We have to say, okay, this is fine, this is very nice. When do people die and what happens to consumption and how do things evolve? So as I said before, we're going to assume that consumption follows a Poisson process. These are Poisson arrivals. Lambda C is the arrival rate. And the impact of the kth arrival is phi sub k, and this is IID across k. So we'll look at the log of consumption, little c, a small letter means a log. And log consumption grows at the normal rate, g times t, minus these Poisson events. So Q is just a Poisson counting process. At the kth event, capital C is multiplied by this random variable e to the minus phi, okay? And now we're going to introduce, we work with this cumulant generating function because it's going to turn out to make everything very simple. We're going to introduce the cumulant generating function, all right, for the consumption process. And it is the log of the moment generating function. Theta is the moment. So it's the log of the expectation of consumption to the theta. Theta is a placeholder variable. And so this is the cumulant generating function. Here now we're writing it with e to the little c. C is the log of consumption, theta, okay? And with this works out very nicely because we're assuming that the events are Poisson arrivals. This means the log of consumption follows a Levy process, okay? And that means that the cumulant generating function is linear in time. So the cumulant generating function over any period of time is the one period function times time. So it means that we don't really have to keep track of time. We can simply worry about the cumulant generating function for one period. And this is what it is, all right? It's just g times theta plus lambda c, the arrival time. This is just a Poisson process. The expected value of e to the minus theta phi. Phi is the random drop in consumption, okay? And phi is a representative member of the independent shocks. So this turns out to be very nice, very simple. Population, we're going to do the same thing. So here's log of population. This is the normal population growth rate, little n. And of course, this can include normal deaths. You might say, well, what about normal deaths, you know, that are not related to catastrophes? We're going to put all of that in little n. So n is population growth, net of normal rates of death. And these are the Poisson arrivals, and psi is the size of the event. And we write down the same kind of cumulant generating function, the corresponding cumulant generating function. We call it kappa. And it is simply going to be, again, the log of the expected value of population to the theta. And again, it scales linearly with time, so we can write it. All we have to worry about is the one period value of this thing. This is what it looks like. Once again, we have psi is a representative shock from the IID shocks. And we can do one more thing. We can say that the expected, by taking this thing and just exponentiating, the expected population, set theta equal to 1. The expected population is e to the cumulant generating function using 1 instead of theta times t. And we can write this way as e to the nt minus lambda squiggle times t. And lambda squiggle, which is just the Poisson arrival rate times 1 minus the expected value of the drop in population, is the death rate, death arrival rate, adjusted for the fact that only a fraction of the population dies, not everybody. So depending on little n, the population growth rate, and lambda d, the population can grow or shrink in expectation. If disasters are frequent, large value of lambda d, they occur often. Or cataclysmic, small value of expected e to the minus psi. And that means psi is big in expectation. And n, the normal growth rate, is low, then the expected population can be declining. All right, so it can fall or rise depending on these variables. If it falls, cumulant generating function is negative. Once again, we're going to use an asterisk to mean that there's no catastrophes. And then n star, the population, just grows at the rate n, little n. This little n is a bad, we should have used a different notation, because we're also using little n with a subscript t to represent the log of population. I'm sorry about that. This little n is just the normal growth rate of the population. All right, suppose there are no catastrophes averted. We don't do anything. We don't do anything to prevent catastrophes, all right? That means there can be a consumption catastrophe in which consumption will drop by a random fraction. There can be a death catastrophe in which population can drop by a random fraction. People die. What is social welfare? This is what it looks like. It's the expectation of welfare for those people who are alive and consume C, and welfare for those people who die. And of course, this changes over time. All of this discounted. So that's welfare. Okay? And again, n star minus n is the number of people who've died. So that looks pretty simple. The nice thing, you might say, well, wait a minute, we need an expectation and we're multiplying n times c, actually n times c to the 1 minus eta. And here again, we're multiplying n times c. How do we take that expectation? Well, the nice thing about this is that because both consumption and population are exponential levy processes, they evolve independently of each other. And that means that the expectation of the product is just the product of the expectations. And that means that we can write the expectation of n times the expectation of c to the 1 minus eta as just e to the cumulant generating function of 1, we're using 1 for theta, times e to the cumulant generating function for consumption at 1 minus eta. Okay? So it works out very nicely. And the same thing for the people who've died. Everything is simplified because these are levy processes. Now, we're going to substitute these things into the integral I just showed you. And then we're going to integrate. And then we're going to rearrange. And this is what we get. Now, this looks a little, I don't know how it looks. This is what we get. And let me just explain it. There are two terms here. The term on the right, the second term, is the welfare flow from the guaranteed consumption stream that you get even after you die. And we're discounting this at the rate of delta minus n. We have to account for population growth. All right? So this is the welfare of the people who've died. This is their guaranteed consumption stream. On the first term is the additional welfare of the people that don't die. So of course, the people who don't die, it's 1 minus epsilon to the 1 minus eta plus epsilon to the 1 minus eta, which is 1. This is the additional welfare, the additional consumption. And this is being discounted at a greater discount rate because of the risk of death, because these people could die. So we're discounting this at the rate delta minus the value of the cumulant generating function, which is greater than n. Okay, and now what we can do is take this and we can figure out what the willingness to pay is. How do we do that? All we're going to do is set one of the lambdas equal to 0. So if we want to get the willingness to pay to avoid a consumption catastrophe, we're going to get the welfare if we set lambda c equal to 0, but account for the fact that we're going to give up a fraction WC of consumption. So for example, to get the willingness to pay to avoid the consumption catastrophe, we're going to replace the cumulant generating function by the version of it when there's no catastrophe, which means just G, the growth rate of consumption times 1 minus eta. There are no catastrophes, consumption catastrophes, but we account for the fact that we're sacrificing a fraction WC of consumption, always. That's what the willingness to pay means. It's the willingness to pay is what is the most we're willing to give up, sacrifice of consumption, okay? So this is the welfare. We're giving up this fraction of consumption, but now lambda c is 0. So we take this thing and we equate it to this v, and solve for w sub c. Got it? And that gives us the willingness to pay. And to get the willingness to pay to avoid a death catastrophe, same thing, lambda d is 0. And to avoid both, we set them both equal to 0. And then we we reduce consumption by w sub c and d. All right. What are these willingness to pays? We do this, and here's what we get. Now you're going to look at this and say, well, what a mess, but you'll see it's really not. So here's what we get. The willingness to pay, these three willingness to pays, WTP, satisfy these equations. So we have these terms, A, B, and C, these fractions that are all functions of the cumulant generating function. The star means when there's no risk. No star means there's a risk of a catastrophe. Consumption, we multiply A, B, and C. Death, it's just C, and so on, all right? And we can show that the willingness to pay to avoid both a consumption catastrophe and a death catastrophe is less than the sum of WC and WD minus the product. In our American Economic Review paper, we showed that the willingness to pay to avoid two catastrophes, column 1 and 2, is less than the sum of the willingness to pay to avoid number 1 plus willingness to pay to avoid number 2. This is actually a stronger statement. And this also applies to our earlier paper. We just didn't see it back then. So, you know, as we've always explained in all of this work, willingness to pay, these WTPs do not add. And they do not add because utility, social utility, is declining. And so when you have a catastrophe, it affects overall utility, which affects the willingness to pay to avoid something else. Okay, now these look messy, but in fact, what we're going to do is assign probability distributions to phi and psi. These cumulant generating functions, these apply to any probability distribution, anything you want to write down. They're completely general. But to apply this model, which we want to do, we need to write down a probability distribution, and we're going to assume that these shocks are exponentially distributed. All right? And that says that the expected value of phi, the consumption shock, is 1 over beta C, and the expected value of psi, the drop, if there's a death catastrophe, the number of people that die, the fraction that die, is 1 over beta D. So that says that a large value of beta means a not such a bad catastrophe. Not that many people, not that big a consumption loss, not that many people die. Large value of beta C means we don't expect bad things to happen. Small beta C, bad news. Then these catastrophes are very bad. Okay?
Hi, Bob. Hi, Bob.
Go ahead.
I have a question. So this is Cynthia Lindell. This is absolutely fantastic. I have a question. So I'm trying to map what you're saying into sort of literature on discounting when we're talking about growth. And so here, for example, the growth rate of the economy, the G that you have is an IID a variable, and I assume like the mean and the variance here are known, and what's sort of uncertain, well, so that's IID, but the mean and variance are unknown. And then when we have these shocks, the phi and the psi add some uncertainty to that. And I'm wondering if you could talk about how that maps into, for example, people who think about, when we think about the growth rate, that maybe either the mean is unknown or maybe the variance of that growth rate is unknown. Here, if you think of that G in your model with those parameters as known, but we have these additional shocks that perhaps are exponentially distributed, is there like a way we could frame it in that framework? It's as if we had the structural uncertainty that this variance was unknown, or is it like, does it map that way? I guess that's more on the discounting literature, but it helps, like, this is like fascinating just to think how the VSL and willingness to pay is like related to some of the frameworks people have used to look at discounting. Thanks so much.
Okay. I didn't pay Cynthia to ask that question, but I guess I should have paid her to ask that. I'm glad she asked it. I'm going to talk about discounting, but I want to wait a little bit, and we'll do it in the context of the exponentially distributed shocks. So I'll show you what discount rates look like, okay? So let me go on here. This is, and by the way, the nice thing, again, about these cumulant generating functions, we can write down any distribution we want and find the cumulant generating function. And then work with it. And the cumulant generating function can be written generally as just a series. There's a series solution for it. We can look at different cumulants. So it's a very nice way of handling uncertainty of risk of any kind. We're using a very, very simple representation of the shocks. Now, given these distributions, what happens to the cumulant generating functions? Very simple. You know, if there's no risk, if there's no consumption shock, no consumption risk, it's just the growth rate times 1 minus eta. If there's no death risk, it's just n, the population growth rate. And if there is risk, we have to include the Poisson arrival rate and the characteristic of the shock. And what we're going to do is define two things. I'm going to define rho. Rho is delta minus n plus g times eta minus 1. Now, we're also going to define some adjusted arrival rates, which I'll get to. This rho, now we have Cynthia's question. This rho is actually a discount rate for consumption, not utility, but consumption. And it's a discount rate. We have to subtract the population growth rate. Because remember, our process for consumption is per capita. So we have to subtract the population growth rate from the rate of time preference. This is the consumption growth rate times eta minus 1. So this is actually a discount rate. And what about these things? Lambda C prime, lambda D prime are risk and impact adjusted arrival rates. So look at the death lambda D. Lambda D is the arrival rate of a death catastrophe, a pandemic, whatever. If we divide it by beta D plus 1, we're going to make this number smaller. And the bigger is beta D, the less severe is the death catastrophe. A large beta D means the average population drop is smaller. Okay? Well, that's like simply not changing beta D, but just lowering the arrival rate. Keep beta D the same, but lower the arrival rate, and you'll get the same thing. We can work with an arrival rate divided by a shock rate, kind of a impact rate, or an adjusted arrival rate. Lambda C prime, we're also adjusting for risk. So here, because consumption gives you welfare, gives you a benefit through constant relative risk aversion, here we're taking into account risk aversion. And the larger is eta, the larger is going to be lambda C prime. We're going to increase this lambda C if we increase eta, and decrease it if we increase beta C. So what we can do is simplify things by working with these risk and impact adjusted arrival rates. Okay. Now, plug these in, all right? And this is what the willingness to pay, the WTPs, look like. And again, they may look messy, but these are just parameters. I mean, you're just adding some things here. Look, the death rate row, which we just talked about, this is this discount rate plus the risk and impact adjusted death rate, arrival rate, the consumption arrival rate, and so on. Epsilon comes from the VSL. Epsilon, remember, this depends on S, which is the VSL parameter. Okay? So everything boils down to a set of parameters that we can try to calibrate. What do we need to calibrate? Because now we want to apply this. I want to apply this to pandemics and macroeconomic risk. Well, we need the events. We need the catastrophes. The consumption catastrophe is characterized by two things: the arrival rate and the impact parameter, beta C. That's it. The death catastrophe, the pandemic, the arrival rate, and beta D is the impact parameter. Okay, that's it. We need the VSL, S. We need to know what the VSL parameter is. Well, there's a huge literature. We can take it from that, but we can also think about it a little bit. And then we also need to know what's the coefficient of risk aversion, the rate of time preference, N and G. N and G are easy. Those are historical numbers. We can get those from data. Eta and D, well, there are a number of ways we can get that. I'll talk about that in a moment. So we need to come up with these numbers to calibrate this thing. If we can come up with these parameters, we can calibrate this model and then apply it to things like macroeconomic risk, recessions and pandemics. And that's what we're going to do. Pandemics. We wrote this before COVID. And what we did is we looked at all of the pandemics that existed in the last 100 years. The biggest one was the Spanish flu. And by the way, the numbers you've seen for the Spanish flu, there are many, many studies of the Spanish flu that put the death rate in the United States, the immediate death rate, people just drop dead, and the later death rate, they get very sick and they die 3 or 4 months later, at 4% of the US population. And there's some studies that put it even higher. Anyway, we look at the Spanish flu, and there were a number of much smaller pandemics that occurred over the last 100 years. We looked at all that data, but not including COVID. All right, this is written pre-COVID. And we came up with a value of 24 for beta D, which means that the expected impact of a pandemic could be lower, could be higher, is 4%. The arrival rate, 0.02, means every 50 years on average. We said, look, the CDC, and if you look at the paper, you'll see the quotes from the CDC. The CDC, well before COVID, this is 2 years ago, the CDC said, and before Trump got involved writing what the CDC says, the CDC said that yes, nowadays there's a much higher risk of a pandemic. It is amazing to read what the CDC wrote just 2 or 3 years ago. The CDC wrote that animals are going to transmit this stuff to humans. There's a much greater rate of animal to human transmission. The mutation rate is greater. The transmission rate is greater. People are flying on airplanes. They're moving around. They're on crowded buses. And we are going to have this, and the words of the CDC are something to the effect of, it's not a question of if, it's a question of when, and it could be much worse than the Spanish flu. So it's really interesting to go back and read what the CDC wrote just a couple of years ago before there was any COVID. This is coming, they said. Just wait, it's coming. So we said, okay, let's put in a high risk scenario. Let's double the arrival rate. We'll keep the impact the same, but let's double the arrival rate to 0.04, okay? What about economic risk, macro risk, recessions? We're going to use the numbers from Barrow Ursula, their 2008 study. They looked at about a panel of about 30 or 35 countries. They also looked at the United States, and they looked at contractions of 10% or greater. So they said, look, anything less than 10% is not a disaster. No big deal. They only looked at contractions of 10% or greater. Now, what we did is we took their data and their numbers and we adjusted them so that they apply to any contraction of any size. If you look at the world data, the 35 countries or whatever, you get an arrival rate of about 0.08 and an impact parameter of 7.3. And that says that you're going to have a, part of this is, you're going to have a contraction roughly every 13 years on average, and an average size of about, what is it here? I can't see. Of about 12%, okay? Then we looked at what they did for the US, but they wrote that this was published in 2008, so we added the 2008 recession. And there were a lot of studies done that showed that for the 2008 recession, the contraction size in the US was 10%. That gives a much higher arrival rate, but a lower impact. It says that the arrival rate is 0.29, the contraction size is 18.6. That says that we're going to have a contraction every three and a half years on average, with an average size of only 5%. Now, turns out, I'll show you some graphs, but it turns out this is worse. Because even though the average size is smaller because it's more frequent, over the next 50 years, a world with these numbers is worse than a world with the numbers here, with 0.08 and 7.3. So we're going to call this R2, we're going to call this the more severe high risk scenario. We're going to look at two scenarios, a low risk one, which is P1, pandemic 1, and recession 1, R1, and a high risk scenario, which is pandemic 2 and recession 2, okay? And let's see what they say. So first of all, I just want to show you, these are the shock characteristics for the 4 shocks. And the red lines are pandemics, and the black lines are consumption catastrophes. This is on the right side, the expected total loss over some horizon T. And you can see that the more frequent, that's the dashed line, the more frequent recessions that are smaller in magnitude have a much greater expected loss. Now you might say, well, wait a minute, hey, hang on here. The expected loss here for pandemics doesn't look that bad. It's way down here. But these are deaths. And a death turns out to be pretty bad relative to you lose some consumption, okay? So these are the characteristics of the 4 different catastrophes we're looking at, the 2 versions of the pandemic and the 2 versions of the recession. Okay.
Hi, Bob.
Yes, go ahead. I was about to say, anyways, anybody have a question? Go ahead, Cynthia.
Yeah, thanks, Bob. So if I understand correctly, your consumption catastrophe, your recession, and your pandemic, your death catastrophes are 2 different catastrophes. So in particular, with a pandemic, it may cause death to some, but no consumption loss to others who aren't who don't die because of the catastrophe. And your thought experiment when you're comparing averting one or the other versus both, when you're thinking of averting both, is averting 2 different events. And I'm wondering, for example, in COVID, it's causing death for some, but also recession and sort of consumption loss for everyone. I'm wondering if how sort of the calculus, if there's an event that might potentially cause both, and when you're thinking of averting things that might have, these things might be correlated. Thanks.
Yeah. So when we did this, we looked at the Spanish flu, and it turned out GDP in the United States didn't change. I mean, noticeably, there was no significant change in the Spanish flu. Now, you're quite right. COVID is certainly having a huge impact on the economy everywhere in the world. And but we can handle that. We didn't here, but we can do it. And if you look at our 2015 paper, we allow for this. We allow for catastrophes that are interrelated. So here, the interrelationship is that a death catastrophe also causes a consumption loss. So we can do that here. I mean, we didn't. It complicates the math, but we can do it. We haven't, but we could. And before I go on, any questions about what's going on here so far? Or is this pretty clear? Okay. So we need values for the coefficient of risk aversion, the rate of time preference, the normal growth rate of consumption, per capita consumption, and the population growth rate, and the VSL parameter. And we're going to use values for eta and delta that are broadly consistent with the macro finance literatures, but also with the disaster literatures. And so I wrote a paper with Neng Wang from Columbia on disasters. And what we did is, rather than put in data for these parameters and for the disaster arrival rates, we backed those things out from a general equilibrium model. So we built a general equilibrium model, and then we said, look, based on this general equilibrium model, and based on we used the first 4 moments of stock returns. And we said, what is the implied coefficient of risk aversion, and what's the implied rate of time preference? And we came up with these numbers, that eta is around 3, and the time preference is around 0.05. Barrow did a similar exercise, looking at what's consistent with the data, and he found, a coefficient of risk aversion of around 3.5 to 4, and a rate of time preference of 0.05. The macro finance literature, they put eta at around, again, 2 to 4, 5, and delta 2, 3 to 5 or 6, 0.05 or 6. We're going to use 0.05 for delta and 3 for eta, but we'll vary these a little bit and see what happens. Okay? US data puts the growth rate of per capita consumption, real per capita consumption, at 2%, and population growth 1%. We're going to set S at 7. That's the number that the EPA and the Department of Transportation use to get, that gives you a $10 million, $10 to $11 million VSL. It's in the mid-range of most estimates, and that gives you this expression for epsilon to the 1 minus eta. Very simple. Okay. Now what we're going to do is we're going to calculate the willingness to pay to avert each type of catastrophe, a consumption one, a pandemic, and both. But we're also going to calculate what I'm calling WC prime and WD prime. What is that? WC prime is the willingness to pay to avert a consumption catastrophe, ignoring death, ignoring pandemics, making believe they couldn't happen, okay? And WD is the willingness to pay to avert a pandemic, ignoring economic risk, ignoring recessions, all right? We want to see what background noise does. In other words, how does the risk of a recession affect the willingness to pay to avert a pandemic, and vice versa. We're going to see it's actually pretty significant. Okay. Again, two sets of calibrations. The low risk, these values of lambda C, beta C, lambda D, beta D, and the higher risk calibration. And now we just calculate these results, and here's what they look like. So on the left side, we're fixing the VSL parameter at 7. And we're looking at how the willingness to pay varies with the coefficient of risk aversion. This is the low risk scenario. Now, the blue lines down here, this is the willingness to pay to avert, the dashed blue line to avert the pandemic. And it declines and then increases, but it's pretty high. It's around 10% or more. This is what it would be if you didn't have any macroeconomic risk. It would be quite a bit lower. Macroeconomic risk has a big impact on the willingness to pay to avert a pandemic. The pink lines up here, this is the willingness to pay to avert economic risk, recessions. And down here, the dotted pink line is the willingness to pay if there was no pandemic risk. And once again, you see that pandemic risk significantly affects the willingness to pay to avert economic risk. And this black line is the willingness to pay to avert both consumption and pandemic risk. And these numbers are pretty high. You know, you might say, oh my goodness, how could it be that society would be willing to give up 20 to 25%, you know, in that range of consumption in order to avoid macroeconomic fluctuations, recessions, macroeconomic risk? How could it be that we'd give up that much? Wow, I taught this morning and I thought if I don't teach in a big classroom, it wouldn't be so tough on my vocal cords, but it was. So anyway, these numbers for the willingness to pay are actually consistent with the whole consumption disaster literature, this huge literature on consumption disasters. The welfare effects of macroeconomic risk are large, very, very large. And they're especially large if you think the coefficient of risk aversion is high, 4 or 5. So these are high numbers. Macroeconomic risk imposes very, very high welfare costs. This is what comes out of all of the consumption risk, the disaster literature, okay? But we're also getting pretty big numbers for pandemic risk. Here, we're varying, we're holding eta at 3. We're fixing the coefficient of risk aversion, but we're gonna say, look, wait a minute, maybe 7 is not the right number. Yeah, I know that the Department of Transportation thinks the value of a life, it should be 10 or 11 million dollars, but maybe that's not the right number. Maybe it's bigger, but maybe it's smaller. So we're gonna vary S. And by the way, the literature, which is huge, puts S at anywhere between 3 and 10. 7 is kind of in the middle. Well, obviously, if you reduce S, you're going to reduce the willingness to pay to avert a pandemic. No surprise, all right? And we're going to come back in a moment and ask, well, given these numbers, does that tell us anything about the value of a statistical life and what the correct number ought to be? So we're going to use that to look at this question of how do we think about a reasonable number for the VSL? But this is what happens when you vary S. This is the low risk scenario. Now let me turn to the high risk scenario. So here's the higher risk scenario, and not surprisingly, all the WTPs go up. Take pandemics. Here we're varying eta, but we're fixing S to be 7. And you can see that the dashed line here, this is the willingness to pay to avert a pandemic. You know, it's around 20% of 20% of consumption. It's a very, very high number. If you didn't have economic risk, if there were no recessions, no macroeconomic risk, would be a lot lower. But it would still be pretty significant. It would still be, you know, depending on ADA, 15, 10%, 8% of consumption, a big number. So this says that if you think the high risk scenario is a reasonable scenario, if you're okay with these parameters, then you would think, you would agree that we ought to be paying a hell of a lot of money to avoid pandemics and to avoid recessions, to avoid macroeconomic risk. Not clear how we can avoid macroeconomic risk, but we ought to do it if we can. All right? And here we're varying, once again, on the right side, we're varying the VSL parameter. We're fixing the coefficient of risk aversion at 3. We're varying S. And as you'd expect, when you lower S, the willingness to pay to avert a pandemic goes down. But you know, even if you make S equal to 3, make it equal to 3. The willingness to pay to avert a pandemic in this case is about 10%. We should sacrifice 10% of, if we could, 10% of consumption. We should be willing to sacrifice 10% of consumption to avert future pandemics. And by the way, if we include COVID, we have to recalibrate this model. These lambdas are going to go up and the betas are going to go down. Got it? Now, this is simply the interdependence. And this is a point we emphasized in our earlier paper. These catastrophes affect each other. The WTPs are interrelated. You know, you can't look at catastrophes in isolation. And so this is a way of looking at that. We're looking at the ratio of the willingness to pay to avert a consumption catastrophe, ignoring the pandemic, to the willingness to pay when you don't ignore it, likewise for the pandemic. And you can see that that really makes a difference, right? Really makes quite a difference. All right, what's going on? First, we're getting very high values of the willingness to pay to avoid macroeconomic risk. And again, here we're eliminating macroeconomic risk. We could complicate this model and do it for a reduction in risk. We could say, what's the willingness to pay to reduce lambda C from whatever the number was, cut it in half, or increase beta C, make recessions less severe. We can do that very easily. I mean, you know, it's a little messy in the arithmetic, but we can do it very easily.
Say, Bob.
Here, we're just eliminating it. Larry, go ahead.
Yeah, on this issue of reducing risk versus eliminating it, one of the nice results from your earlier paper, which I assume applies to the new paper, is that if you got a whole bunch of potential catastrophes out there in general, you don't want to go after all of them. However, if you could reduce risk rather than eliminate it, so in that sense, wouldn't that result change that you'd basically want the marginal payoff to be the same and you go after all of the catastrophe possibilities?
So yes and no. So yes, if you can reduce it, these ratios will not be as big. In other words, if we look at simply cutting the lambdas in half, instead of setting them at 0, these ratios won't be as big because we're not having as big an expected impact on future utility. But what we show in the other paper, the AER papers, you can't just look at, there's no marginal anything anymore. You can't look at the marginal benefit. Marginal things don't work in this world. That's what's interesting here. That's why we called the paper The Strange Economics of Scylla and Charybdis, because there is no marginal this equals marginal that. The rule for what catastrophes to avert is actually a combinatoric problem. It's not setting marginal benefit equal to marginal cost. That cost benefit rule breaks down. That's the interesting thing here. It breaks down. Okay, so look, we're finding a very high values. Again, it depends on which calibration you look at, for the willingness to pay to eliminate, and it would also be high to reduce macroeconomic risk. But we see that these costs are partly due to other catastrophes. Now, in this paper, the only other catastrophe we're worrying about is pandemics. That turns out to be pretty big. But, you know, we could add others. We could add nuclear terrorism, you know, all the things I love to think about. Nuclear terrorism and other terrible things that could happen. Here, it's just pandemics. The economic risk also raises the welfare cost of pandemic risk. I mean, the willingness to pay to avert a pandemic could be a third lower if we eliminate economic risk, economic fluctuations. But actually, before I get to that, again, the willingness to pay, the high willingness to pay to avoid macro risk is consistent with a long literature. This is not something that, wow, where did that come from? These are numbers that people are getting in this consumption disaster literature. Now, even for the low risk calibration, we're getting a willingness to pay to avoid pandemics around 10% of consumption. That's around $2 trillion per year for the United States. We do not spend anything. I mean, we spend essentially nothing relative to this number, nothing. All right. Now, you might say that we're using too high a value for S, for the value of a statistical life. Yes, when people are asked questions about, would you take a job in which your probability of dying, you know, goes up by 1% or whatever, how much more would we have to pay you? And when they answer these questions, or we look at the actual choices they made, it looks like the marginal rate of substitution gives a VSL of $10 million or whatever. Okay, it looks like that, an S of 7. That's what seems to come out of people's decisions when they're making choices involving very, very small changes in what are already very, very small probabilities. Now we're asking, well, wait a minute, can we aggregate this when we're looking at something that could kill 4% of the population? Is it still reasonable? Now, let's think about this $10 million VSL. It says that the value of the US population in total is $3,300 trillion, which is 6 times the 500 trillion present discounted value of GDP over the next 40 years. So you got to ask, well, where does that 3.3 quadrillion dollars come from? 3,300 trillion. Where's that going to come from? What does this mean to say that I personally would be willing to give up $10 million to avoid death, to avoid a death? Okay, fine. I mean, you know, I'll get MIT to cover it, to cover the 10 million. Can we do this for everybody? Where does this come from? What does it mean? So we have a problem here in that the VSL simply does not aggregate. Secondly, it looks at people's choices, these choices they make, let's say over jobs or where to live. You know, they do this also. Do you live in an area where there's a greater risk due to the environment, greater risk hazard from environmental risk? And again, these are very small probabilities and very small probability changes. Very different from saying, look, you know, what's your life worth and what are we going to pay you for you to stay alive, okay? And so maybe we're using a VSL number that's too big. You know, if you look at this, because but even if you have an S of 2 or 3, even if you say that the value of a life is not $10 million, it's only 3 million, all right, or 2 million. It says that the willingness to pay to avert pandemics is 4% to 9% of consumption, depending on which scenario we use and depending on the coefficient of risk aversion. Is this unrealistic? Is it crazy to say that, let's take 5%, to say that a willingness to pay to avoid pandemics is 5%? Well, remember, the willingness to pay is a reservation price. This is the most society would pay, the most society would be willing to pay to achieve a goal. In this case, the goal is to eliminate pandemics. It's like you buying a cup of coffee, that first cup of coffee in the morning. What would you pay? What's your reservation price? It might be $20, $40, but you don't have to pay that. Depending on where you are, you only pay $2 or $3 for that cup of coffee. So a reservation price doesn't mean this is what you actually pay. And there have been studies done, again, CDC's got great stuff, go look at it, on what it would cost to reduce the risk of pandemics, not eliminate, but reduce. What it would take. A lot of people have looked at this, and what they find is it would not take 5% of consumption. It would not take $1 trillion a year. 5% of US consumption is about $1 trillion a year. It would not take that. It could take much less. Now, the fact is that what we're spending is close to zero. We are spending right now close to zero on reducing, never mind eliminating, reducing pandemic risk. In fact, the budget of the CDC has been cut. It was cut in 2017, 2018, 2019. It was just cut again. The proposed budget for the CDC has been reduced again during COVID. So we're spending, and we've left the World Health Organization, the WHO. So in terms of the United States, we're spending, a good approximation is zero. That's a pretty good approximation to what we're spending to reduce the risk of future pandemics. And you might argue that maybe that's not right. Maybe it shouldn't be $1 trillion. Maybe it should only be $10 billion or 100 billion, but not zero. Anyway, let me stop here and get some questions, discussion, whatever. I think it's about 5:30. So am I sort of on the schedule here? Jing and Claire, is this about right?
That's terrific. We'll open it up to questions.
Okay, so let's questions, criticisms, whatever.
Hey, Bob, on that last point about how little the US is spending on this, you would say the same thing about climate change, and both pandemics and climate change are global externalities.
Yep.
So I'm wondering if, maybe a better comparison would be how much are we spending on forest fires or something like that, something that's local.
That could be, yeah. I mean, you're right, pandemics are global. These are global catastrophes. Pandemics are almost always global. That's why the World Health Organization is important. That's why part of what the CDC does, those of you may not know this, the CDC is a US agency, but in fact, it works internationally. And it does surveillance, it has an international surveillance program. It's very big, it's a big part of their budget. So in fact, the CDC looks internationally, but you're right. These are international, these are global potential catastrophes. And actually, since you brought up climate change, look, let's add, I think nuclear terrorism is a huge catastrophic risk. It's global, that too is global. We can come up with a bunch of them that are global, but you're right. We might want to compare it. We have to think about it in that context. Cynthia, is your hand up? I can't.
Yeah. Hi, Bob. So thanks so much. So I have a question about thinking about that risk aversion parameter eta in your constant relative risk aversion utility function. And so I know you said you're not, you thought about using Epstein's in, but you stuck with this more sort of elegant approach here. The risk aversion parameter does sort of play, I guess, 3 possible roles, because it's not only risk aversion, but it's related to intertemporal elasticity of substitution, and also sort of piggybacking on Chris's point about sort of global and thinking society level. I mean, it's also thinking about intergenerational inequality aversion. And so I'm wondering, so I guess I'm wondering what you're thinking is that is primarily capturing here. And also in particular, when you had those nice plots of willingness to pay versus eta, the risk aversion parameter holding S fixed, it was kind of monotonic. And I was wondering if you could, the intuition for that was not obvious to me. And I was wondering if you could maybe talk through what might be going on there. Thanks so much.
So there are a few things here. So first of all, just one thing, you're right. The coefficient of relative risk aversion is the inverse of the elasticity of intertemporal substitution. And the whole advantage of recursive preferences, Epstein, Weil, Zinn, don't forget Weil in there. The whole advantage of EWZ preferences is that we separate risk aversion from the coefficient, from for intertemporal substitution. We keep them separate, okay? We used, Neng Wang and I used EWZ preferences, recursive preferences in our paper back a ways. It makes life very complicated, but we used it. And I have very mixed feelings about it because we don't know what the coefficient, there's a lot of information about the coefficient of relative risk aversion. You may not like the data, you may not like the studies, but a lot of studies. There have been studies of the elasticity of intertemporal substitution that put it all over the place. I mean, the numbers range from 0.1, 0.2 up to 2 or 3. Huge variation. We don't know what it is. The other thing is that if you think it's a big number, and the long run risk people think it's a big number, they think it's above 1, then that says that you'd be willing to pay a lot of money for the early resolution of uncertainty, even though you can't do anything about it. So you have to understand, recursive preferences means that you're willing to pay to find out what's going to happen in 5 years, even though you can't do anything to change what's going to happen. You can't change your portfolio, for example. You're going to find out that there's going to be a deep, deep recession in 2 years. The stock market's going to drop from whatever to close to 0, but you're not allowed to sell stocks as a result. And it finds that people are willing to pay a huge amount of money for that. And that to me doesn't seem very realistic. So I have sort of I wouldn't say mixed feelings, negative feelings about recursive Epstein-Weil-Zinn preferences. And here they just really muck things up. I mean, it just makes things very, very complicated. Actually, it always makes things very complicated, but here we gave up on it. In terms of the behavior, the dependence on ADA, yeah, it's complex, and there are a bunch of things going on here because it affects how a drop in consumption affects your welfare. That's pretty direct, but it also affects things because it enters into epsilon, the amount that your consumption drops when you die. Remember, when you die, your consumption doesn't go to 0, it goes to epsilon times what it was when you were alive. And that epsilon depends on ADA. And that's why you don't get this simple, actually here you see even better, you don't get that simple monotonic relationship. That's what's happening. Other questions or thoughts about this? Larry?
Well, I'm hesitant to say anything because I was hoping a lot of other folks would be asking questions, but if not right now.
They're shy. People on the West Coast are much more outgoing and
well, one quick comment and a quick question. The quick comment, I think Chris makes a good point about public goods aspect here, but I don't think you also mentioned what might be another point why we don't see nearly as much being paid to avoid disasters as what you would suggest. And that's simply lack of information and denial. Maybe I missed that, but to me, that's very important. People don't want to believe that things like this can happen, or maybe they haven't done the research to see that they could. Anyway, that's the comment. The question is, back early in your talk, you mentioned you alluded to the fact that it's really hard to know how to model the utility or lack thereof of someone who's dead. And you mentioned there's 3 ways that it could be done, and that the ways you haven't done it pose serious computational or analytical problems. Nevertheless, I still have a little hard time thinking of a utility, apart from the bequest issue, by the way, coming from someone who's dead, to someone who's dead. So could you perhaps comment on how the treatment of that utility could be influencing your results? If you took one of those other 2 approaches, would that change the results a lot?
Well, it might. We could certainly do, what Hall and Jones did and simply assume the utility goes to 0. It would constrain things. Remember, we don't assume a utility function when you're dead. We assume a utility function when you're alive, and we derive the utility V of W when you're dead. We derive that. We don't assume it, we derive it. So it requires constant relative risk aversion when you're alive, and that's what gives you constant relative risk aversion of a smaller amount of wealth when you're dead. So that comes out of the definition of the VSL. right? It comes right out of the expression for the VSL. So, you know, we're looking at, I'll just say two things, then I want to go to your first question.
Let me just ask this to make sure.
Social
You're saying this is
utility.
an ex-ante valuation of utility that I give if I die in the future, as opposed to the utility I'm getting once I'm dead. I can understand the first being positive. The second being positive is a little harder for me.
All right, well, we're going to ask some dead people and see what we find out. Look, no, this is social. Remember, looking at social utility here.
Okay.
And social utility means that people who are dead, they have bequests, and the government takes money and redistributes it. Look, and if you go back to the early studies,
The bequest part, I'm fine with the bequest part. I'm talking about the other part.
Yeah, you go back to the earliest studies that from which VSL came from, Sherwin-Rosen and so on. All of it is based on this utility of life, living, utility of the dead in the dead state. They don't say the utility of the dead, they call it in the dead state, which somehow maybe that's different, I don't know. So that's always there. It's inherent in this whole value of life literature.
Okay.
Let me go back to your first point. Do we simply ignore this stuff? So there was a book that Richard Posner, the judge and economist, he writes a book every year. He wrote a book, I don't know, 10, 15 years ago, 10, 12 years ago, called Catastrophe. And he talks about all terrible things that could happen. And I love those kinds of books. You know, all the big catastrophes that could happen. An asteroid could hit, terrible things. And his point in that book is we don't do anything. We ignore this. And we should be doing a lot. And I agree. And I think the problem here is that humans don't like to think about this stuff. They don't like to think. My wife doesn't like it when I talk about this. And they don't like it when people talk about all the terrible things that are going to happen or could happen. We avoid this. Secondly, it means spending a lot of money. And we don't like to spend a lot of money. You know, you're going to ask me to give up half my consumption in order to prevent climate change and nuclear terrorism and pandemics. And what's wrong with a little nuclear terrorism and climate change? I don't want to give up a lot of consumption. So people don't want to pay for it. They ignore it. I think it's built into our psychologies, and then they don't want to pay for it. It's too bad. But I think that's how it is.
But Rob, I mean, isn't there a bit of a, I think it also depends on the last few pandemics, right? We had SARS, we had MERS, we had like Ebola, and none of them really took off. So I think if you were to ask people and poll them over time and how much they're willing to pay, it would dramatically change now that we had sort of a huge outbreak. But it's too late now, but there's sort of this myopic updating. We had 3 pandemics. We sort of managed them with, I mean, there were some dead people, but it wasn't really, not even close to what the current one is. And so that will change, obviously.
You know, you're absolutely right. There were these earlier pandemics, and, you know, people say, well, I don't know many people who died from that. And you're absolutely right. And that affects people's perceptions. Remember, the calibration we did here was pre-COVID data. We didn't include COVID. We looked at the last 100 years through the Spanish flu and all the little pandemics that happened, or epidemics, whatever you want to call them, over that 100 years. We didn't even include COVID to get this calibration. So, but you're right, people don't think about it. And if you tell them about the Spanish flu, you know, that's ancient history. I mean, World War I, and I mean, that's like another world. They don't think about it.
Bob, one of the catastrophes that you didn't mention, but a former colleague of mine at Hoover did study, was asteroid colliding with the Earth. And actually, he came up with numbers that were quite sensible in terms of how much it would cost to avoid or set up a asteroid defense force. Now, over the past several months, I've participated in many seminars, and one of the things on COVID, and one of the things that some of my colleagues like to emphasize, in particular one who went off to Washington recently, was that the COVID deaths are primarily old people. And what's the value of life for an old person? Now, I don't remember hearing you say anything about age specificity,
Right.
but this is with COVID or flus in general, this is a among people who are, let's say, not concerned about political correctness, this is a big topic that's always brought up, that, the people who have economically valuable lives aren't dying. So what's the big deal?
Right. So that's right. So you're absolutely right. But just let me correct one thing. You said with flus in general, and that's not true. So the Spanish flu disproportionately killed very young people.
Yeah.
Most flus, bad flus, kill disproportionately children, actually, infants, children, young people, not older people. In fact, it's very strange. They don't understand why COVID is disproportionately killing older people. We don't understand it. Because it doesn't jibe with other viruses, other flu-like viruses. And some of these are corona-type viruses.
Yeah.
So, but you're right, in terms of COVID, it kills mostly older people. And, who cares? Look, that's the solution for climate change. We get rid of these older people. They're exhaling carbon dioxide and, maybe it's not so bad.
But now do you think that a age-adjusted approach to what you're doing would yield significantly different results?
Well, it would for COVID, but it wouldn't in general, because again, COVID is the only pandemic I'm aware of that disproportionately kills older people. And in fact, for other flus and Spanish flu and so on, it's disproportionately younger people who have many years to live. So I don't, for COVID, but not in general. I think Claire and Jing, I think it's your job, given the nature of this seminar, to hand out antidepressants to everybody.
Sorry, Bob. We'll have to virtually send them out somehow.
Put them in the mail.
But I think, so this is nearing the time when we would have officially ended and then said, oh, the casual chat is starting. So I'll just take this opportunity to thank everyone who joined us today, and particularly thank Bob for being our first speaker of this multi-university series. So I want to say to everyone who's still here that our next seminar is November 16th. It's also a Monday, and the speaker will be Marshall Burke. The title will be Pollution Exposure Disparities and Their Implications. So for more perhaps depressing topics, stay tuned from this series. And with that, thank you everyone, but we'll stay on or keep this channel open for everyone.
So I'll stay connected, and then anyone who wants to stay, just stay.